Good day, I'm Charlene Mayra Retardo and I'm going to discuss about nonlinear programming. So first, as we recall, um, in linear programming, our goal is to maximize or minimize linear functions subject to linear constraints. Um, it is the same. It is the same goal with nonlinear programming, except that um, nonlinear programming is more complex. Linear functions have the form of sum product, and if the a linear programming problem is feasible, then at least in theory it can always be solved. But sometimes the objective function may not be a linear function, or some of the constraints may not be linear constraints. That's why we have nonlinear programming. Next, introduction to nonlinear programming. First, optimization problems that involve nonlinearities are called nonlinear programming problems. Nonlinearities occur when, for example, two entities in which change in one entity does not correspond with the constant change of another entity. Second, many nonlinear programmings do not have any constraints, and these are called unconstrained nonlinear programming. Third, solutions to NLPs are found using search procedures. Solutions are more difficult to determine compared to linear programming. One problem is um, difficulty in distinguishing between a local and global minimum or maximum point. So a local optimum is a feasible point that has a better value any other feasible point than any other feasible point, while global optimum is the point with the best value of the objective function wherein the anywhere in the feasible region. And last one, real life applications include product mix problems with price elasticity, transportation problem with volume discounts, and minimizing risk with risky securities. Next, um, nonlinear programming problems are very complex to optimize, and these are some of the reasons why it is hard to optimize. First, as we discussed earlier, it's hard to distinguish a local optimum from a global optimum. It's hard to distinguish a local optimum from a global optimum because numerical methods for solving nonlinear programs have limited information about the problem. Second, optima are not restricted to extreme points. Um, there are limited numbers of places to look for the optimum in a linear program. We need only to check the extreme point or corner points of the feasible region polytope. But in nonlinear programming, this is not the case because an optimum could be anywhere at an extreme point along an edge of the feasible region or in the interior of the feasible region. Third, there may be multiple disconnected feasible regions. Um, there may be multiple different feasible regions because of the way in which nonlinear constraints can twist or curve. Fourth, different starting points may lead to different final solutions. This is related to the way in which nonlinear solvers work. One very common algorithm chooses a direction for search and then finds the best way of the objective function. Fifth, it may be difficult to find a feasible starting point. In linear programming, we need to find the point that satisfies all of the constraints. But in nonlinear programming, there is no such guarantee that all constraints um, are going to be satisfied. Six, it is difficult to satisfy equality constraints. Um, it is the same with number 6, and in nonlinear programming, finding a solution that satisfies curving and twisting equations is difficult in itself. And last, there is no definite determination of the outcome. Um, in nonlinear programming, you are never really sure whether the model is actually infeasible or if there is feasible solution found. Next are the graphical illustration of nonlinear program. In the first example, we maximize z equals to 3x sub 1 plus 5x sub 2, which are subject to the following constraints. X sub 1 less than or equals to 4, 9x sub 1 raised to 2 plus 5x sub 2 raised to 2 less than or equals to 216, and x sub 1 more than or equals to 0, and x sub 2 more than or equals to 0. This example is a nonlinear constraints when the optimal solution or an approach that best fits the situation is not a corner point feasible solution. Next. Second example, we maximize z equals 126 x sub 1 minus x sub 1 raised to 2 plus 182 x sub 2 minus 13 x sub 2 raised to 2, which are subject to the following constraints. X sub 1 less than or equals to 4, 2x sub 2 less than or equals to 12, 3x sub 1 plus 2x sub 2 less than or equals to 18, and x sub 1 more than or equals to 0, x sub 2 more than or equals to 0. This example is the same with the first example, except that the it has linear constraints but nonlinear objective function when the optimal solution is not a corner point feasible solution. And lastly, the third example, we maximize z equals to 3x sub 1 plus 5x sub 2, which are subject to the following constraints. X sub 1 less than or equals to 4, 2x sub 2 less than or equals to 14, 8x sub 1 minus x sub 1 raised to 2 plus 14x sub 2 minus x sub 2 raised to 2 less than or equals to 49, and x sub 1 more than or equals to 0, and x sub 2 more than or equals to 0. This example is when a local maximum is not a global maximum, or the feasible region is not a convex set, meaning the two sets of points are not connected and it has dents around the perimeter.
Vanessa Tricia Lascuna, I'll be reporting about the types of nonlinear programming problems. So, nonlinear programming have mentioned earlier, so it is the process of solving optimization problems where the constraints or objective functions are nonlinear. Yung constraints, ito yung mga restrictions or limitations on the decision variables. So the first type is unconstrained optimization. It says here the function of x1 has no functional constraints. For example, f in general. The variable m is equal to 0, means non-constraint. So hinahanap lang dito yung minimum or maximum ng given variable considering na yung minimizing objective function, nakadepende siya sa real variables with no restriction. So, sinusolve mo yung problem as unconstrained problem. So, the result will be unconstrained optimization. So, next is linearly constrained optimization. It says here, it has two functions, the objective function nonlinear and the functional constraints nonlinear. So, yung objective function nonlinear is ginagamit lang siya for large scale, and they say that functional constraints linear is efficient. So, yung purpose lang nitong dalawa is to calculate the least value of the real function. So, next is yung quadratic programming. It says here that special case of linearly constrained optimization when the function is quadratic. So, masasabi lang yung function is quadratic kapag it has multiple variables, yung objective function at saka yung constraints. So, for example, yung x sub 1 minus 1 is greater than 0, equivalent to constraint 2 2x sub 1 minus 1 equals to 0. Therefore, the integer program is formulated as quadratic. Next is yung convex programming. It says here that it covers a broad class of problems and the local maximum is a global maximum. To summarize all the types of nonlinear programming problems, the variable p sub 0 up to p sub m will result to positive or semi-indefinite. Therefore, it will give you to a result of convex programming. If variable p sub 0 up to variable p sub m will result to neither positive or negative, therefore, it will give you to a non-convex programming. And last, if variable p sub 1 up to variable p sub m is equals to 0, it will result to a linear, and if it is multiple, it will be quadratic programming. Next is separable programming. It is a special case of programming. Special case of convex programming. Separable programming, ito yung special case ng convex programming. Yung function ay yung variable ng f and g are separable functions, then the decision is appeared to be separable. Next is yung non-convex programming. It says here that even if we are successful in finding the local maximum, there is no assurance that it also will be a global maximum. In some special cases, the problem can be reduced to an equivalent convex programming problem. It highlighted here that in fractional programming, when both the numerator and denominator are linear functions, it can be transformed into an LP problem or linear program. So, sinasabi lang dito, yung non-convex programming, tulad ng sinabi ko kanina na yung kapag yung variable p sub 1 up to variable p sub m, kapag will result to neither positive or negative, it will be convex. So, the price given, yung price na given, na identify mo lang siya as the maximized profit. Next one is yung single variable unconstrained optimization. Dito lang nagpapakita na kapag simple yung equation, gagamitin yung function df over dx equals to 0. And for linear or quadratic functions, gagamitin yung df over dx. So, under nun is yung example. Given yung fixed cost na $7,500, the variable cost per unit for $40, the price per unit, and the demand with the equation V equals 400 minus 1.2p or price per unit, then it will result to maximize profit. So, given na dito yung function V times P minus CF minus V times CV. So, Z as the profit equals to 448p minus 1.2p with the function, using the function of the demand, equals to 0. So, the price per unit is 448 over 2.4 will result to 186.66 or $187. So, the demand, yung $187 is ilalagay lang siya dun sa demand function. So, 400 minus 1.2 times $187 is equals to 18,313 shares. So, makikita sa gilid yung graph na maximize using the price per unit na 187 is na maximize natin yung profit. That's all. Thank you.